Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. And today I wanted to go over the different BJT amplifier configurations. So the goal here is to understand the different configurations for an amplifier. We have what is called a common base, so you have a common base amplifier type, a common emitter with emitter resistor, and a common collector with emitter follower. So each of these has different characteristics. You have the voltage gain, you have the input resistance, and you also have the output resistance. So the goal for, depending on what you want, if you want an amplifier that has good gain, you want to have a high input resistance, and the output resistance you want to be low so that it doesn't attenuate the signal. So usually you want the gain to be pretty high. If you want to have current amplification, usually the common base is used for that current amplification. And for the gain, it would be a positive GM RC. For the input resistance, is going to be 1 over GM. And for the output resistance, it's going to be your value for RC. So you can see here, to get a high voltage gain and you want a low output resistance, these two are going to contradict themselves. And so it's hard to get that quality from a common base. So usually that's why it's used for current amplification. So the next type of configuration is called a common emitter. And the common emitter has the gain of a minus GM RC. And R pi is the input resistance, which a lot of times you can try and get that to be a pretty high number. And then RC is also the output resistance. So again, these two kind of contradict themselves because you're not able to control that RC and have it be both a high gain and a low output resistance. So a lot of times you'll cascade amplifiers, use a common emitter or a common emitter with emitter resistor as your gain, and then a common collector with emitter follower as the next stage. This one has, usually you can design that to give you a gain of approximately 1, and it has a low R out and a high R in. So again, the common emitter has the highest gain, and it has a relatively low R in though and a relatively low R out, but usually that doesn't give you the higher gain. So most of the time you'll have that be a high gain, but then have a high output resistance and a lower input resistance, and then cascade it with this common collector to give you a more of the quality of amplifier that you want. So the other equations, this would be the gain equation for the common emitter, and then you can see the input resistance and output resistance, and then also those for the voltage gain, the input resistance, and the output resistance. So these equations come from the actual amplifier itself. So let's start with the common base. So this is a configuration that I'm recommending you all use for your amplifier design. It is a biased configuration so that you can put the transistor needs to be in active mode. So in order to amplify an AC signal, you have to have that transistor stay in active mode and not move into the saturation region. So that a lot of times is determined by that RC value. So active mode is determined by your DC biasing. So the DC values need to be such that for an NPN you have that VB is less than VC. And so you are going to design this amplifier to create that, and I'm going to go through that in a different video, what those values and how to find those. Once you get those biased correctly, then you can look at the hybrid pi model. And so the hybrid pi is already drawn here. And what you're going to do to create each of these amplifiers is that you are going to connect the input to a certain location, and that is also going to determine where your output is. So for a common base, the common means where your value goes to ground in the hybrid pi. So for base, you're going to connect a capacitor to ground right there at the base. In the hybrid pi, that is going to create a ground at the base, which is going to basically short out R1 and R2. And so this will give you what you'll have for the hybrid pi. Your input is going to come in, and you connect each of the AC by a capacitor, which is going to filter out any DC coming in from wherever your source is. So your input in this case comes in at the emitter side, and your output comes out at the collector side. So here, when I connect this, I am going to put this right in parallel to the RE, so it's going to bypass the RE itself and go right into that emitter side. And so this is going to be the AC signal that comes in here. You can then see that V pi is a minus Vn, and your output at VO is just going to be a minus GM V pi RC, and the V pi is a minus Vn, and so you get V out over Vn. The minus is canceled to give you positive GMRC. So that is where that GMRC comes from. Your output is going to be where your output is located. So our out is here, which, as you can see, is just RC. And your input is going to be right here at the emitter side. So it is going to ignore the RE because it's bypassed by the Vn. And all you're going to see is from the resistance reflection that 1 over GM. And so that is where those values come from in the equation set. So for each of these, the configuration is, again, wherever it says common. So for common emitter, you're going to put a capacitor in parallel to the emitter. And that gives you a ground in the hybrid pi, so that bypasses the RE here. Your input for this one goes right in at the base. And your output goes out at the collector again. So for this one, your input is right here at the base, so that is in parallel with R1 and R2. So you can see with this at ground, you have Vn is equal to V pi. And again, VO is a minus GM V pi RC. And so V out over Vn is a minus GM RC. And so that gives you the gain equation. Your input goes in right here, but you're bypassing the R2 and R1 just because they're right in parallel with that Vn. And so all it sees from here to ground is V pi, and so V pi is your input resistance. And then again, your output resistance is here, so it just sees RC. So those are the values for the common emitter. For the common emitter resistor, you leave the RE and don't bypass it with a capacitor. So again, the input will be at the base, and your output will be at the collector. And so again, your input this time is going to have the resistance reflection rule, so you have R pi plus beta plus 1 times RE, so you get a higher input resistance, and that's the advantage of this one, but your output voltage is a little bit lower because you have to, you have the division of the 1 over GM plus RE. So it's slightly lower than what you can get from the common emitter, but you can still get a higher resistance. And then RC is your output resistance unless you calculate it with RO. And this would be the equation with an RO in parallel. So for hand analysis, we usually just make the assumption it's about RC, but you can see that it will be very different with RO, and usually from the simulation you can get that value, which is easier than doing it by hand. The common collector, you're going to bypass the collector with a capacitor. And so here you'll have that connected to ground, so that will bypass the RC. And for this one, you're going to have the input still at the base. And your output for this one will be at the emitter side. And so you can go through again the hybrid pi. This will be in parallel to R1 and R2. And your output now will be taken here, and you can calculate that to get the approximate gain here. And again, the input resistance has the R pi times beta plus 1, and now you have RE in parallel with the 1 over GM because of the value that's seen here at the emitter. And so the common collector, usually you can't quite get a gain of 1, so you can design this and you get about 0.8 or 0.9, but you try and get a goal of around 1 for that. So for each of these configurations, we saw above kind of the advantages of each one. And then I showed you in the design where to put the capacitors to create these different configurations. And as I said before, you can also cascade these, so you can put a common emitter first and then a common collector right after it, so that you can have a high gain. And then another word for the common collector is a voltage follower, which you guys are used to that configuration for the normal dual input amplifiers, and that's what the common collector acts as, is a voltage follower. So a buffer is another word for that one. All right, thank you for watching this video.